All right, guys, so we're going to pick up in the second half of Module 11, talking on page 394 about ideal gases. So we learned about the combined gas law, right? And that's extremely useful, but it can't be used or it can't be applied to all gases in all situations. So in order to use the combined gas law, that gas has to behave in an ideal manner. Okay, well, what is an ideal manner? Your book gives you three properties right here. Okay, so number one, the molecules or atoms that make up the gas are very small compared to the total volume available to the gas. Number two, the molecules or atoms that make up the gas must be so far apart from one another that there's no attraction or repulsion between them. And then thirdly, the collisions that occur between the gas molecules or atoms must be elastic. So when the molecules collide, no energy can be lost in that collision. Okay? So in order to use the combined gas law, you need to know that you're working with an ideal gas. And the way to know that is to know that gases behave ideally at high temperatures and low pressures. Okay? So what exactly is a high temperature and what's a low pressure? Well, standard pressure and temperature, STP, would be a temperature of 273 Kelvin right here and a pressure of 1.00 atm. So that's kind of your measuring stick for the standard. So a gas with a temperature that's close to 273 Kelvin and a pressure that's near or close to 1.00 atm will behave in an ideal fashion, okay? So under those conditions, you can use the equations that we've talked about, okay? In this module, I just wanted to highlight one thing. A gas with a temperature that's close to the standard, the 273 Kelvin, or higher than that, and a gas with a pressure that is near 1.00 atm or lower than that. I left that out in the previous. And we're going to move on right here to Dalton's law of partial pressure. So when two or more ideal gases are mixed together, the total pressure of the mixture is equal to the sum of the pressures of each individual gas. Okay, so basically right here, PT, P total, that's your total pressure of your gas mixture, is going to equal your P1, which is the pressure of gas 1, plus P2, which is your pressure of gas 2, plus P3, which is the pressure of gas 3, etc. Okay? The pressure of an ideal gas does not depend on the identity of the gas. It depends on the quantity of that gas. That's a really important part from this module. And then, okay, moving into vapor pressure. Have you ever left a glass with a little bit of water on a counter and let it sit overnight? What happens in the morning? Well, the water can be gone. If it's just a tiny bit under the right circumstances, why? It can evaporate. Well, why? Well, the water can go from its liquids phase to its gas phase, right? But how? If you didn't boil it, if you didn't boil that water away, what caused it to go from that liquid to the gas? So think back to the kinetic theory of matter that we talk a lot about in class, right? The water molecules in the gas are moving around and they can bump into each other, right? Some bump into the glass that it's in, and some move faster than others. And those that are moving faster and faster, if they make it to the water's surface, and if they're going fast enough, they're actually able to escape the liquid, okay? And enter into the gas phase. So evaporation happens because some liquid molecules move fast enough to escape the liquid surface if they have enough energy to do so, okay? This is actually always occurring. There's always going to be water molecules near the water's surface, and some will be going fast enough and have enough energy to break through it or escape, right? So at any given time, there's going to be some vapor sitting atop that surface of a liquid, and it's going to be made up of the molecules that have escaped the liquid by bolting up out of the surface, okay? And then they're going to be in that gas phase. Because all gases exert pressure, every vapor layer will exert some pressure too, okay? So, and then they define vapor pressure right here for you. It's the pressure exerted by the vapor that sits on top of any liquid. Okay, so if you were to have a container of liquid, you know that some of that liquid's molecules exist in the gas phase right above that liquid surface, okay? And the pressure that that vapor creates then is called the vapor pressure. And vapor pressure is going to be different based on the chemical nature of the liquid, okay? So let's say you had water, right? You're going to have a pretty low vapor pressure because it doesn't readily evaporate, okay? It's harder for it to evaporate. But then if you were to have a container that has rubbing alcohol in it, that has a larger vapor pressure. Why? Because it easily evaporates, okay? Another thing to note is that vapor pressure of any liquid is dependent on temperature, okay? So it talks about that over here. For water, as the temperature increases, so does its vapor pressure, okay? So the vapor pressure of any liquid increases with increasing temperature right there. That's a big point to remember. And then to figure out the vapor pressure of a liquid, we need to know what the liquid is as well as its temperature, okay? And if you look at table 11.2 right here, it gives you the vapor pressure of water. You can see how vapor pressure increases with increasing temperature, right? So it gives you vapor pressure and temperature, and as it increases, you can see that it increases as well. Water boils at 100 degrees Celsius, right? And the pressure right here is 760 torr, okay? So another thing to note is that 760.0 torr is equivalent to 1.000 atm, okay? Boiling point is defined as the temperature at which the vapor pressure of a liquid is equal to the normal atmospheric pressure, okay? So the boiling point of water is 100 degrees right here, and it's equal to 1 atm or 760 torr, okay? You may have heard that water can actually boil at a lower temperature when you're at higher altitudes, and you can kind of see why now, right? At higher altitudes, your atmospheric pressure is lower than 760 torr, and so the less atmosphere above you pushing down on you, right? So you can see how that you can have a situation in which that could happen. Chemists often produce gases with chemical reactions, right? Collecting the gas above the reaction. Often, this is done in the presence of water. The gas bubbles out of the water and is collected in a container like a balloon or something like that. When a chemist does this, we say that the chemist is collecting the gas in the presence of water, and that means you need to consider water vapor as one of the gases that's also collected. Example 11.2 says a chemist produces hydrogen gas in an experiment and collects that gas in the presence of water. If the total pressure of gas collected was 1.115 atm and the temperature was 26 degrees Celsius, what was the presence of hydrogen gas collected? Okay, and this is going to be pretty simple, right? PT equal P hydrogen plus P water vapor. Okay, so we know that our PT is 1.115 atm because they tell us that our total pressure of gas collected. Okay. Then we don't know what our P hydrogen is, but we do know what our P of water vapor is because we can get it from the table 11.2. If you go back here and you look at your temperature, you can get 25.2 right here. For temperature is 26, it's going to be 25.2 torr. Okay, so this number right here is going to be 25.2 torr. So remember, 1 atm equals 760.0 torr, right? So I can convert my 25.2 torr to atm. So I'm going to have 1.115 atm equals my P hydrogen, which I don't know yet. And then over here, they go ahead and convert that for you. 25.2 torr, and then you times it by 1 over 760 torr. They cancel out, and you get your ATM, which is 0.0332 ATM. So then you simply take 1.115 ATM, you subtract your 0.0332 ATM, and you get that your P hydrogen is 1.082 ATM. Okay? So it's a pretty simple formula, pretty simple way to do it. So hopefully that makes sense to you. All right. Now looking at an alternative statement of Dalton's law. So another unit of concentration is the mole fraction, right? So mole fraction is only used when there's a mixture of gases abbreviated as X right here. So X equals the number of moles of the compound over the total number of moles in the mixture. So if you have a mixture of gases containing 3.0 moles of oxygen gas right here, and you have 5.0 moles of nitrogen gas and 1.0 moles of neon gas, what's the mole fraction of each component in the mixture? So you can set this up. My X oxygen is going to be 3.0 moles over 9.0 moles. My X nitrogen is going to be 5.0 moles over 9.0 moles. And then my X of neon is going to be 1.0 moles over 9.0 moles. And then if you were to work this out, 0.56 and 0.11. Okay, and right now there's no units because the moles cancel, right? So the quantities without units are dimensionless quantities. These are dimensionless quantities. So if you add up these three amounts, they should equal 1, right? Or close to 1, depending on significant figures. So 56, 89, and they do. So basically what this is telling you is that for every 100 molecules or atoms in this mixture, 11 are going to be neon, 56 are going to be nitrogen, and 33 are going to be oxygen. Okay? And yes, that's exactly what they did there. So hopefully that makes sense. All right. And then the equation right here, P1 equal X1 over PT. So P1 is your partial pressure of a gas, okay? X is the mole fraction of that gas. And then PT is the total pressure of the gas mixture, okay? Example 11.4 works through a problem on how to do that. Let me know if you have any questions. I'm not going to just write it out now, but let me know if you have any questions or if you don't understand it. I suggest working through some practice problems of this. We get to the ideal gas law. All right. So PV equal nRT right here. And P is pressure of the gas again. V is the volume, okay? N is the number of moles of the gas. T is its temperature. And R is the ideal gas constant, which you do have to memorize. And it is right up here for you to memorize. R is equivalent to 0.0821 liter times ATM over mole times Kelvin, okay? So make sure you're paying attention to units when you're working out your problem. Things should cancel out. If you have a temperature in Celsius, you're gonna need to convert that. If you have torr, you're gonna need to convert it to ATM when you have an R, okay? So pay attention to those units. All right, guys, originally I had planned on doing this experiment for you, but I'm not sure I'm gonna be able to do it. So please, please, please read through this experiment as well as the other one and make sure you understand what's going on, what the point of them are. You do not have lab reports on them, but it's still important to understand why they have these in the modules where they do and what concept you're learning from the experiments. So don't short it just because I'm not showing it here. Please read through it and understand it. Okay guys, I thought it might be helpful real quick to go over the review questions for this module before you take your test. So they're on page 416. So number 1, define pressure and name 3 units used to measure it. So you guys know that your book defines pressure as the force per unit area that a gas exerts on its surroundings, okay? And there's different units that measure it. There's ATM, torr, we talked about millimeters, mercury, mmHg. There's also Pascal, kilopascal. You just would need to name 3 of those, okay? Number 2, write Boyle's law in your own words. So there's going to be a lot of different variants here, but basically Boyle's law states that under conditions of constant temperature, the product of a gas's pressure and volume will be constant, okay? Number 3, which of the laws you studied in this module leads to the Kelvin temperature scale? Okay, we did this in class, and the Kelvin temperature scale is derived from Charles's law, okay? Number 4, what general rule must a careful scientist follow when extrapolating data? Again, we talked about this in class heavily. A careful scientist can extrapolate data only when you have a large amount of data compared to how much you're extrapolating. So you need a lot of data, a little extrapolation, okay? Number 5, what are the properties of an ideal gas? So we just talked about that in this video, but the molecules that make up an ideal gas must be small compared to the volume available to the gas. The molecules or atoms must be so far apart they don't attract or repel each other. And also the collisions that occur must be elastic. Okay, number 6, under what conditions do gases behave ideally? Gases behave ideally when their pressure is near or lower than 1.00 atm and when their temperature is near or higher than 273 Kelvin. Number 7, what are standard temperature and pressure? STP is defined as 1.00 atm, atmospheric pressure, and 273 Kelvin, okay? Number 8, 2 steel containers of equal volumes contain 2 different gases at the same temperature. The first container holds 1.3 moles of nitrogen gas, and the second contains 1.3 moles of SO3 gas. Compare the pressure of the 2 containers. So Dalton's law tells us that the pressure of an ideal gas is independent of what it is, right? It's independent of its identity. So they're both actually going to have the same pressure. Okay. Number 9, a liquid's temperature is lowered from 50 degrees Celsius to 10 degrees Celsius. Did the liquid's vapor pressure increase, decrease, or stay the same during that time? So remember, when the temperature of a liquid is lowered, its vapor pressure is lowered as well. So the vapor pressure will decrease. And the last question, the mole fraction of nitrogen gas is in compressed air is 0.78. If you have 1,000 molecules of compressed air, how many will be the nitrogen molecule? Okay, well, if you were to have 100, it tells us that 78 of those would be nitrogen. So if you were to have 1,000, you're just going to multiply it by that factor. 780 of those are going to be nitrogen. You let me know if you need help. So what you guys need to do is you need to take this test. And I would suggest taking this test this week. This test will be due when you come back the week after spring break. So not next Monday, we don't meet, we have spring break. But the Monday after that, you are responsible for bringing in your Module 11 test to me that day. And you need to have read the entire Module 12 coming to class. I don't think that's too much to ask you to do. You have some time. I understand you're going to want to take spring break off, and that's fine. So work this week and get done what you need to get done. Let me know if you have any questions, if there's any problems that you need help with before you take your test, anything like that, let me know. I'm available, and good luck.